Welcome to the IDS lecture featuring innovation and discovery in the Division of Engineering and Applied Science at Caltech. My name is Ravi Ravichandran, and I am the chair of the Division of Engineering and Applied Science. Theodore von Karman, a Caltech legend and the founder of JPL, once said, "Engineers create the world that never was." This is indeed one of the goals inspiring the engineering faculty and students at Caltech. And the purpose of our IDS lecture series is to highlight the engineers and scientists whose research focuses on fundamental discoveries, innovations, and inventions that can power the transformative technologies of the future that will create knowledge for the ages and benefit the society. Today's IDS lecture is the first in the series. I am delighted to introduce Dr. Axel Scherer, the Bernard A. Netjes Professor of Electrical Engineering, Medical Engineering, Applied Physics, and Physics. Axel received his PhD in 1985 and worked at Belcore before joining the Caltech faculty in 1993. His interdisciplinary research focuses on micro and nano systems fabrication of optical, electronic, and fluidic devices with applications ranging from microcavity lasers to biomedical devices. Axel's group is currently focused on integrating nanoscale vacuum tubes for high-frequency electronics and works on the application of wireless chips with electrochemical and metabolic sensors for the purpose of building injectable health monitors. Axel is a prolific inventor and holds over 120 patents. In recognition of his innovations and inventions, he was inducted into the National Academy of Inventors in 2015. Over the past 2 decades, technology from his group has been commercialized through several startup ventures in telecommunications and healthcare devices. I now invite Axel Scherer to present his IDS lecture on point of care everywhere.
Thank you very much for this wonderful introduction, Ravi. In this webinar, I would like to share with you some of the work that has been done in my group over the last 20 years on developing point-of-care medical diagnostic tools. And what we really mean by point-of-care is the place where the patient meets the medical system. Typically, that's the doctor's office or the pharmacy or the dentist. And the idea is, in this case, to build systems where we can diagnose and triage patients right there on the spot. And this is not able to be done a lot today because we are using centralized laboratories, and we have to oftentimes ship samples to these laboratories to get before we can get our answers. And that provides us with a logistical problem that recently has been really exasperated by the pandemic we're all in. So I'd like to show you in this lecture some of the work that we are doing to address that and what we hope to do with the medical transformation, changing from a centralized system to a distributed diagnostic system. The work that I'm going to be sharing with you really has been done by a lot of people, a lot of students and collaborators, and I'd like to acknowledge them all ahead of time right here. There are too many to read out. And those are the people that really did most of the work. I get the benefit and the pleasure to present it to you. And I'd like to split the talk into 3 different pieces. The first one, I'd like to introduce the fundamental technologies that we're dealing with, microfluidics, for example, or qPCR pathogen detection. Then we'll go into applications. In particular, we'll look at two applications. One is detection of COVID-19 in a point of care setting, as well as then also metabolic testing. And so what we'd like to do is start by explaining to you where the technologies are that we're using. So as a backdrop, I'd like to sort of remind everybody that it's a big challenge to provide medical care. And in fact, the cost of medical care has increased over the last 50 years by about 800%. And of course, we live longer than we did 50 years ago, but the cost is actually rising and in an alarming and unsustainable way. And the idea is that we might be able to use technology, in particular consumer electronic type of technology, and lithography and the techniques that we have learned from consumer electronics to decrease the cost and to make diagnostic tools available more widely than they are right now. The idea really in my group has been to develop miniaturized devices, and we obviously started with electronics and optical devices, and more recently we've worked on microfluidic devices and miniaturizing and reducing the cost of medical devices. What's interesting is when you lithographically define these things, you can start integrating them, and you can build systems that are optoelectronic or optofluidic. And that integration allows us to really build systems that are much more functional. And so we've been using the historic capabilities of the microelectronics industry and started applying them to the medical applications. And so about 20 years ago, Steve Quake and I developed microfluidic systems like this one. This is a mixer that's made by essentially replication molding little channels. And we include valves and pumps. And the unusual part about this is that the valves have a picoliter or so dead volume, so you can control the quantities of materials, of reagents within a picoliter very accurately. If you take 3 valves in sequence, you can make a pump. And in this kind of system, you can pump around materials and control reactions very accurately. This is the concept of microfluidics. And so we've started using these kinds of systems and try to integrate them into solutions for medical applications. And of course, the idea is to build systems that do the same thing as our modern diagnostic tools, but do them in a smaller form factor, are fully automatic, so they don't need the infrastructure of a clinical laboratory to function, and are cheaper. That's the hope. Of course, as you miniaturize these systems, you also have some advantages and disadvantages. And this is a long journey, and we're just at the very beginning of it. So the opportunities here are to use this kind of technology that we've built to make these systems. So 15 years ago, we built systems like this. This is what we would call a laboratory on a chip, and it has 2,000 valves, and its purpose is to build RNA libraries of different cells. So if you have, in this case, 32 different cells, you can load them into this chip, and you can lyse the cells, extract and purify their RNA, and then amplify it using a PCR reaction. So the idea is to do all of these things and get an RNA library of 400 molecules or so that we collect and amplify them and compare them. And it's all done on a single chip. Now, unfortunately, the chip, even though it's very small, it's about it's an inch by an inch. The infrastructure that's required to run it is quite complex. You need a fluorescence microscope, for example, and you need a whole bunch of electronics to control the valves and the pumps that are on the chip. And so in a way, even though this is a very small and very powerful device, the problem is that it's really not, it's much too complicated in order to be used in a point of care type of setting. So if you will, this is a chip in a laboratory rather than a laboratory on a chip. Another type of system which we developed for the for blood tests is shown here. This has about 600 valves, and it's a sandwich assay chip. It actually can look at 10 different patients at the same time, or 10 different samples at the same time, and measure 4 different concentrations of proteins in these 10 patient samples. And the idea is that it can do these things in parallel and speed up what normally would be a long blood test. Again, in this case, we use fluorescence to measure the concentrations. And because it's a microfluidic system that allows us to pump the surface, the sample over the functionalized surface very efficiently, we can actually get very sensitive results. So we get clinical concentrations, relevant concentrations of about 0.1 nanomolar of these different proteins that we might be interested in. But again, even though it's a very powerful chip, it requires this fluorescence microscope to provide us with the information that gives us then the concentration that we're measuring. And again, it's pretty complicated. And so what we decided to do more recently is to get rid of the fluorescence microscope. And we did that by changing the paradigm of how we measure to measure refractive index changes. So for example, we have a silicon photonics device here. This is an optical resonator that is made on a wafer scale SOI wafer. And it basically allows us to measure the refractive index of its surrounding. So as you have a binding reaction that binds proteins onto this resonator, you change its path length, and you can actually measure how many molecules you bound. And one of my former students, Kerry Gunn, started a company based on this. It's called Genolite, and it does this very thing. It has a resonator, a silicon photonics resonator, and we basically, this chip actually measures the frequency at which this resonator works. And it can measure inside of this box, basically the concentration of biomarkers and proteins. So this starts to look more and more like something you could use in a pharmacy or a doctor's office. So again, it's a little expensive solution and it's very specific, but the idea is getting closer to making something that can have the cost and the capabilities and the automation that's needed. I'd like to give you one last example of what we can do in the lab, and that is a surface enhanced Raman spectroscopy. It's one of my favorite techniques because it allows us to see single molecules if we want to. And the idea is that you have a laser beam that gives you light at a very specific wavelength, very accurate single wavelength, and you scatter that laser beam in the material of interest, in tissue samples or whatever you're looking at. And the idea is that the light from the laser, these photons, because of your scattering, they lose energy, and you can measure then by looking at the energy loss, you can measure the vibrational modes and the bonding structure that identifies then your molecules that are surrounding your system. The trick in order to do this efficiently is to build systems where you have a very large enhancement, a very large optical field. And we can do that by nanofabrication. So we can generate these extremely high optical fields. And in this case, we use little metal nanoparticles that we fabricate on the surface. These are little spheres of gold, and just about where they meet. So if they're 10 nanometers apart here, these two spheres, generate this extremely high optical field that is 10 to the 10 times higher than the surrounding light. And that allows you to do very efficient Raman conversion and generate then these spectra, which can identify the molecules that happen to be in that area. And so the way that we make these little nanobulbs is by using microfabrication. So we make little silicon pillars. We oxidize those so they become silicon dioxide. Then we coat them with gold, and then we heat this up. And what happens is the gold diffuses, and surface tension forces it to become sort of rounded and forces these tiny little bulbs to occur. And then as you make them bigger, as you wait longer, you generate this surface of very uniform gold balls that have these very high field enhancements. As you reflow the gold, you generate these high fields. We put these on top of the end of optical fibers. The fibers are about the diameter of a human hair, 150 microns or so in size. And this is the surface enhanced Raman spectroscopy field up here. And then that allows us to shine light into it, the laser light. And then it allows us also to extract the scattered light back out and measure it with a spectrometer. So this is a system that when you put it into this injection needle, it allows you to measure real-time chemistry in vivo. And so the high fields are generated and you can measure different compounds. So in this particular case, this spectrum shows you thiophenol that has been deposited on the edge of the nanobulbs. And again, we have this enhancement factor of 10 to the 10 times. And what we're trying to do is use this to measure things that are relevant that you cannot measure any other way. So for example, we know our blood contains thrombin. It's one of the coagulation factors. It's a very important part of the blood factor of the cardiovascular system. But the problem is if you want to measure thrombin and you take blood out to measure it, the thrombin immediately disappears because the blood coagulates. And so in order to measure thrombin, you really should be inside of the living organism. And so fortunately, there is what's called a thrombin binding aptamer that allows us to selectively coat on top of our surface enhanced Raman spectroscopy nanobulbs, these gold particles. And we can then measure spectroscopically the thrombin that way. And so what happens is if we take this thrombin binding aptamer and we measure that in our surface enhanced Raman spectroscope, we actually get this kind of blue spectrum when we look at the scattered light, the Raman spectrum. And then when the thrombin binds to it, you get this red spectrum. It's fundamentally different. It has these different vibrational modes that occur when one material binds to another. So you actually can see the reaction of thrombin onto the thrombin binding aptamer right in real time. We actually tried this out. So we put 500 femtoliters of thrombin into the solution. We start with the thrombin binding aptamer, and after 15 seconds, we started to see a change in that spectrum. And after about 90 seconds, it stabilized into this thrombin plus the binding aptamer spectrum. And what's interesting here is that at this concentration of 500 femtomolar, we have about 1 thrombin molecule every 15 microns, and we're measuring only about 5 micron areas. So we actually see a single molecule, more or less, statistically, reacting with our surface. So this is very interesting because it allows us to observe a reaction while it's taking place in vivo. And then we can, if we wanted to measure thrombin, for example, we would have to desorb it. And we can do that by heating up this material, the end of the glass fiber. And we start with this spectrum that we just saw, the thrombin plus the binding aptamer. And as we heat it up slowly, we actually see first that we go back to just the aptamer spectrum. And after a while, if we go too hot, then the material, the aptamer delaminates. But there is a nice temperature at which we can release the thrombin and then bind more thrombin. And so this is actually a very interesting approach that allows us to do spectroscopy at the nanoscale. So I hope to have convinced you by now that we have developed techniques to measure femtomolar concentrations. We've developed technology to react materials with picoliter accuracy by microfluidic systems. And we have the optical and electromechanical systems, the back ends, to measure very sensitively. So the question is, how do we now take these kinds of ideas and put them to use in real useful systems? So to start with, let me talk about our detection of pathogens. So this gentleman is sneezing, obviously not wearing a face mask. And the question is, nowadays, is he infectious? And in order to find out, we would have to take his nasal swab and we would send it to a central laboratory. And maybe a day later, we can tell the gentleman that either he is infectious or he's not. This is actually unacceptable, I think, because we could tell him with our instruments that the answer within 15 minutes. The reason why we want to do that is because, even though the traditional causes of death in the United States have been heart disease, cancer, and other chronic diseases like diabetes, more recently, just last week, the major leading cause of death in the United States has become COVID-19, unfortunately. And so the question really is, how can we test people expeditiously? And do we really want to wait for 12 hours to 24 hours before we can give somebody an answer? And so in order to deal with this, 6 months ago, we started a company that was based on technology we developed for the Gates Foundation 10 years ago. And the company is called Fast Detect, and it's building PCR machines. And these PCR machines in this system are actually exactly the point of care type of machines that we envision would be useful within a pharmacy, for example. It's a 12-inch tall box, 6 by 6 inches in size, and it has an automatic sample preparation system that allows you to take a raw sample like a nasal swab and convert it into purified RNA, and then it uses reverse transcriptase and amplification to compare that with a standard PCR format. And to remind you what PCR does, polymerase chain reaction, it actually amplifies the number of molecules. So if you have DNA, you can heat it up to 95 degrees, and it splits from its double helix structure into 2 single-stranded molecules. And then when you cool it back down to 55 degrees in the presence of an enzyme and a template or primer, then you can essentially amplify and double the number of molecules every time you heat and cool. So in a system like this, it's important to do this very quickly because we want to do this in 15 minutes so the patient doesn't have to wait. So our system is accurate because it uses the gold standard qPCR technology. It's fast, and I'll show you why in a moment. It's able to be inexpensive and also able to be fully automatic. So that means that you don't need a laboratory technician or a clinical laboratory to do this. We actually accelerated the sample preparation by automation. By doing everything automatically, it turns out that we can do it faster. And the same is true for the amplification. We have preloaded cartridges which have all the chemistry on board, and all we need to do is add the patient sample, and basically put it into the system. We have lyophilized reagents that all are now able to give us a good shelf life. And then when we heat and cool the system, the sample, we actually do it by a cold finger cooling. So instead of using a refrigeration system, we actually have just a cold metal hitting the bottom of the sample to cool it down from 95 degrees to 55 degrees. And then as we retract the metal, we actually then put it onto a heat sink and we mechanically move the heat. So this is done with a solenoid or a relay. It's actually very simple 150-year-old technology that allows us to heat and cool. And we can heat and cool with 15 seconds per cycle, which is relatively fast. That gives us the 10 minutes to 15-minute amplification that we need. At the same time as amplifying, we also watch the fluorescence. We have four wavelengths that we're measuring at the same time. And that allows us to do the negative control as well as a number of different materials. We could look at, for example, COVID-19 as well as other respiratory diseases like the common flu. And then this is the temperature profile. This, you see, it's heating up and then it amplifies. This is the reverse transcriptase. And then we basically can see the fluorescence go up as we do the amplification. And the number of cycles that we have to go to amplify tells us something about the amount of material, virulent material in this case, that was there to begin with. We've compared our system, this one, with the $40,000 commercial system, and we see that our system actually performs the same way with the same sensitivity. And we've gone to clinical labs in Missouri, where we tried the system out on patient samples, COVID-19 patient samples, and we saw that we had the same concentration and sensitivities as the clinical lab did. So this system is actually working now, and it's not been fully optimized yet, but it's working as well as the clinical world gold standards. We've even put assays that are completely commercially available based on the system, and we see the same performance as what the clinicians see. And so in many ways, we now have a system that allows us to perform the gold standard sort of analysis, diagnostics, without the complexity or the cost. So our system costs $2,500. That's at least what we hope to sell it for. And it requires actually just a sample. It doesn't require a laboratory technician. Because it's so simple, we're working on trying to get it completely waived so that it can be located in pharmacies and assisted living facilities and places like that, where you don't have skilled laboratory technicians available. And so you can think about many different places, point of care in the doctor's offices, in pharmacies, in nursing homes, clinics, dentists, airports, schools, and universities, or even at the end of the day, your home. Wherever you want to measure, that's where you could measure it. And the beauty of this PCR machine is that it is not just a COVID-19 detection system. It actually can run any PCR assays that have been developed in the past. And there are many of them for different diseases. So for this country, we care mainly about this particular pandemic right now, but down the road, this system can be used for many other applications. And we can, for example, deal with all the diseases, the pathogens, the infectious diseases that plague 90% of the world, where it's too expensive now at the moment to get a nucleic acid test. And so the idea is this kind of system would be able to be used in the developing world, in the pharmacy. Before I get the antibiotic, I can identify whether I need it. Can also basically make predictions and figure out exactly what kind of medication I need before I have to buy it, by identifying precisely what kind of virus or bacterium I have, rather than guessing it through the symptoms. At home, we can think about using the system to measure ourselves, to identify our diseases, also identify diseases of our pets. There's no problem with testing, so because it's completely automatic. So we could imagine having one of these instruments in our bathroom closet. So the idea is point of care in this case can be anywhere. Okay, anywhere we are, anywhere the patient is, that's where we would do this. Now, of course, we hope that in the near future, in the next year, we can get rid of COVID-19, at least get rid of it to the point where we can go back to semi-normal. And then we have a number of other diseases that still plague us, mainly chronic diseases, heart disease, cancer, stroke, diabetes, also respiratory diseases. All of these are the traditional problems that we have in the medical world, in the developing world. So the question is, how do we deal with those? Well, for those, we have a different solution. We actually have come up with the concept that the ultimate place where we think about point of care isn't the doctor's office, it isn't the pharmacy, it's actually where we are. It's where the patient is. And if we could identify early on symptoms of a disease before it became catastrophic, then we could avoid a lot of the problems and cost. And so, of course, 800 years ago, Henri de Bracton said an ounce of prevention is worth a pound of cure. He was a lawyer, he was not a medical professional, but still, this is a very wise sort of sentence that we should think about. And so we have been thinking about how to use prevention and preventative medicine. And the real possibilities nowadays are to use our technology, the RF tags that we have, the microelectronics that we have, to build sensors that allow us to predict whether we are going to be sick or not. Now, with cars and planes, we already have engine health as a term that identifies how the engine is performing, and we have many sensors that identify that. Our phone has many sensors in it, but we as humans, even though we're very complex organisms, don't have any sensors. Well, our body does, but we can't read them. And so the idea is, why not start thinking about how to build systems that can monitor chronic diseases? And in the past, we've limited ourselves to measuring the temperature, symptoms, rather than the cause, temperature, weight, those kinds of things. And with the exception of diabetes care, we actually are just starting now to build systems that allow us to measure our bodies. Okay, and in diabetes, of course, you care about the glucose level. And so you would have a system that might inject insulin and measure the glucose. To do this properly, what we really want to do is take advantage of our miniaturization, because we want to minimize the size of the sensor that has to go into the body, because we want to inject it. Now this is what we're going to basically, what we've built. We've built systems that allow us to inject a millimeter by a millimeter or smaller devices into the body. We've built systems that have a really high, fast response rate, so you can pulse them, and require very low power, and also are inexpensive. The idea is that instead of having to do blood tests in this kind of machine, we want to do it right in the body. We want to measure our metabolism. So we start with glucose as the first thing that we can measure because there's a large need for that. But we ideally would like to measure many other metabolites. We'd like to measure biomarkers, and we want to measure them continuously because we want to identify a baseline. We want to know for each individual person, there's a difference in concentration. And we basically want to find out the concentration when they're healthy and the change from that baseline, as well as a change in the rate at which things normalize again. So what we want to do, for example, when I measure my lactate level as I climb as I walk up a flight of stairs, I want to measure that level, but then I also want to see how quickly it comes back to normal. And that, I think, is a really much more universal indicator of health than just comparing my concentration with everybody else's concentration. So this is what we mean by metabolic monitoring. What we really need for that is systems that can actually work for long periods of time, so we can establish this baseline, and that are fast enough to follow the concentration changes in real time. One of the things that people do is measure on skin patches. We can measure skin patches and build systems. We've actually built this kind of system that has a little battery on it and has a series of sensors. And this is on a centimeter by centimeter sort of Band-Aid. Call it a smart patch. It measures interstitial material that is iontophoretically sucked through the skin. But the problem with that is it takes time to get the concentration of material through the skin. And so there's a delay in this measurement. So what we really have decided to do much more nowadays is to build systems that are subdermal, that actually are right in the capillary bed of the subdermal material. And there we have a much faster response, and we can measure things, biomarkers, much more quickly. And the idea is to measure these kinds of things with the concentrations, changes in concentrations, with a system that's about 1 millimeter by 1 millimeter in size. This is a smart tag. It's actually a smart tag. It has a antenna on it. It doesn't need a battery. It actually uses a reader that is located on the surface of the skin to power it, and it communicates then through the skin with that reader. These kinds of systems have about 20,000 transistors on them. Azita Imami, my collaborator, is designing these things for us, and we basically functionalize them then to convert them into sensors that measure glucose or lactate, or as I'll show you later, the uric acid and things like that for kidney diseases. The system also has a reader. This is the size of the reader. It's sort of a small handheld thing. And the most important thing is it's made through CMOS electronics. So it's a wafer scale process that allows us to make about 64,000 sensors at the same time on each wafer. And so if you have a typical wafer run of 25 wafers, you can get about 1.3 million devices that are identical, more or less, within the accuracy of the microelectronics fabrication. And so our goal is to take advantage of this scaling with this kind of microfabrication process. If we can do everything on the wafer scale, we can actually make these chips at a cost of about 10 cents per sensor. And that's the goal, is to keep it that way. So that's why I have this device on a 10-cent dime, okay? The idea is that everything we do in order to get there, though, has to be wafer process compatible. So instead of using more common enzyme deposition techniques, we have to use essentially spin coating. Now, spin coating gives you very thin layers, very uniform layers, and we spin coat our enzymes. It took us a while to figure out how to do it, but it turns out it's a very effective way, and it's actually surprisingly, when you make these layers by spin coating, you can go make them much thinner than what you normally would have. And for me, it was surprising that these thin layers are much more efficient. It's actually makes sense because you generate usually the hydrogen peroxide for our devices with the enzyme reactions on the surface of this thin layer, and then you have to diffuse it through the polymer. So it actually does make sense that thin is good. We also have to do vapor deposition systems. We have to deposit the material that encapsulates this, and we do that by vacuum deposition rather than by painting it on. We also had to change away from a battery. We don't use batteries. We just use these RF tags because the battery itself, because it would be very complex to implant it, and it would make the whole device much bigger. So we try to avoid batteries. We just use RF tags. We try to avoid conventional reference electrodes because silver chloride only lasts for about a month. And after that, it strips all the chloride and the silver away. And so instead of that, we use platinum. So we had to reinvent a really old electrochemical system. And we did so by changing materials out, swapping things, but making them compatible with microelectronics. Okay, so for example, platinum, instead of using a normal platinum deposition system that would give you a nice smooth layer, we actually modified everything so that we could get a very, very porous layer to increase the surface area, because the surface area, as shown here, gives you about 100 times more sensitivity and current than you would if you had a smooth layer. So all of these ideas really had to be to then result in trying to figure out the correct vacuum deposition techniques and all of those things to make these layers work well. We also use platinum on top of our enzymes. So we actually have a sandwich of platinum, enzyme, platinum, and the platinum on top protects the enzyme from the body's immune system and from the oxidation. And so all of these systems allow us to have a long lifetime where we need to have about half a year to a year lifetime in order to do our metabolic monitoring. And now we've worked enough on this over the last couple of years. We've developed these systems that now are very robust. They have a very nice long lifetime of about a year. They don't deteriorate much throughout that, so this is a half a year's lifetime. And what's interesting is they actually work better than the traditional systems that are much bigger. And because they're small and because they're thin, everything can happen faster. Diffusion happens faster. And so these devices that we make can give us a reading within 1/10 of a second, 100 milliseconds. Whereas a modern system, if you buy it from Dexcom or Medtronic, you have to typically wait for a minute before you can actually get a good reading. So all of these systems, because they're small, you don't have as much of a scar tissue. You don't have as much of a wound when you inject them. So wound healing is much faster. After day 2, you can't see the device anymore. And the idea is these systems are less invasive, less intrusive, because they're so small. So we've built the smallest electrochemical sensors that we know of. We've generated the fastest results from these. We've gotten very low power out of these devices. We are able to run these very efficiently, and we think we can use CMOS foundries and CMOS techniques to make these devices cost effectively in large numbers. We started by making these devices and hoped that we would get about 2 months, but now we're going towards 6 months to a year of lifetime on these kinds of systems. And that allows us really to look at continuous monitoring of biomarkers. So we've developed sensors really based on the microelectronic fabrication ideas. So the first application actually will not be in humans. The first application we're targeting is going to be in our companion animals, in dogs and cats. In particular, unfortunately, we have a lot of dogs and cats that suffer from diabetes. And the idea would be to measure their glucose by having a sensor injected underneath the skin on the neck, and then have a reader right on the collar. So we have like a smart collar. Unfortunately, because of the lifestyles that we have, we get diabetes, and our pets also get diabetes. They suffer from diabetes. 17% of that cats and dogs ultimately will get diabetes. Dogs, unfortunately, get type 1 diabetes, and so it's much less easy to treat. That's why we only have 170,000 diabetic dogs in this country. Cats suffer from type 2 diabetes, 2 million diabetic cats. And what we are thinking is we can maybe deal with these kinds of diseases by using this technology. Kidney diseases are another key factor in limiting the lifetime of our companion animals. So the dogs and cats both suffer from kidney diseases when they get older. And unfortunately, a lot of the damage of the kidney disease is already done by the time they get symptoms. So the idea is, if we have the capability to measure these, the onset of the disease, then we can treat them right away. And that's the opportunity here. So we can build sensors that look for uric acid, for example, and identify kidney disease early on. So for cats and dogs, this would be very helpful. So there's a number of different disease markers or metabolites that we're targeting. Uric acid, lactate, glucose. We've made all sorts of different markers, and we can think of more. And we're basically trying to figure out how to make our sensors compatible with them and how to test. The questions are, can we make these as uniformly as I suggested by CMOS fabrication? Dogs and cats can help us find out. Can we look at the baseline in an animal, the normal animal, and that we can basically do that too. The idea is we can optimize these systems before we put them to clinical use, and we can identify maybe the biomarkers that we need to watch. And maybe most importantly, in my opinion, one of the most important opportunities is to see what triggers a chronic disease. So for example, in diabetes, we really don't know what environmental factors or other factors may trigger the disease to become chronic. And our furry friends, our dogs and cats, may be able to help us find out. So we can monitor the animals, give them a better life, inject the appropriate amount of insulin, and at the same time learn a lot about our own health. So point of care could be our animals, could be our pets. If my dog has a better health care than I do, maybe the FDA will decide that this is also useful for me. 800 years after Henri de Bracton said an ounce of prevention is worth a pound of cure, maybe we're on the way to finally getting there and building the preventative healthcare in infrastructure. So with that, I just want to sort of highlight the fact that I think we can today build a system where point of care is everywhere. It's wherever the patient is. And with that, I thank you, and I'll take any questions. Okay, yeah, so there's one question. How do you measure the frequency used, given that frequency above 20 kilohertz can't be measured accurately? We actually, so for our implanted or injected glucose monitors, we actually use 800 or 900 megahertz frequencies that the RF tag responds to, and these are able to go through the skin, and power our devices as well as communicate. And we basically use, in the reader, we have a power source that looks at the back reflected power that identifies then a digital signal stream that allows us to identify how much, what the sensor has read in the last microseconds. Now, there's another question, second question: how many different diseases can the fast detect system identify? Does it need to be reprogrammed for the different assays? And if so, how does that happen? So that's a really good question. What that machine is, it's essentially a PCR machine with a sample preparation, with an automatic sample preparation front end. So it can measure pretty much any disease where there is an existing assay for. So if for example, you want to measure tuberculosis or whatever other disease you're interested in, you can measure it with that machine. But you need to, of course, adjust then the primers that are doing the amplification. The other thing that you have to adjust depending on the sample type is the sample preparation. So it's obviously different for a blood sample than it is for the nasal sample. Right now, we're focused on nasal samples because that's what we're doing with the COVID-19 patients. But that's the interesting opportunity there, is that there are many other applications that can benefit from a PCR machine. So this system can actually fit right into the other requirements that people have to measure their diseases. So then there's another question: how many tests per cartridge? It turns out that we can put up to 10 samples into each cartridge. It's called pooling. And so if we have a low prevalence in COVID-19, for example, and we want to measure and screen people as they enter a restaurant or a plane, we can measure many samples at the same time. That allows us to decrease the test cost per person significantly. So cut also the time that it takes to test lots of people. And so this is the whole paradigm here is not only do we have single tests that we can provide, but we can have a screening approach where if you had employees in a dentist's office, you could measure them all at the same time. That would decrease the overall, the individual test cost. Then there's another question, and that is, how does the body react to the injected sensor? That's for of course, the injected devices. What's interesting is the body reacts depending on what's on the surface differently, and also depends on the size. So it turns out the thickness of the scar tissue that forms is oftentimes proportional to the size of the device that you've put into the body. As our devices are relatively small, with 1 millimeter by 1 millimeter, we actually have seen that there's very little scar tissue. It's only 2 or 3 cells thick, and that's a great advantage by miniaturization. There's also the immune response, and the immune response depends on what the body sees. So if the body can identify any strange material that it doesn't like, then it will use organic or oxidizing species to destroy the organic material. It'll assume that it's a bacterial culture. And since we cover our devices with platinum, we actually hide the chemistry from the body, and the neutrophils don't get to see it. So that's actually an advantage with that. So the encapsulation is a problem, but usually it's a problem if you have bigger devices. Then there's another question: have the low-cost PCR machines been used in low-income settings? That's a really nice question. I'd love to see that happen, because I think what will happen is, in the developing world in particular, we'll want to field these devices in places where right now there is very little medical feedback capabilities. If you really think about it, the complexity of moving samples around in the developing world is much greater than what it is in the Western world. So we really should use this opportunity to build systems that can be inexpensive enough to be used in in the developing world. There have been attempts to do this, but unfortunately, it really hasn't been at the scale that's needed. How far has our research progressed on early and continuous detection of cancer biomarkers? It turns out that there are blood tests that have been identified, especially using microRNAs, that are able to identify some cancer types, particular glioblastoma. There's one particular test that uses MIR10B that one of my collaborators is working on. The idea is that if we could identify that in the blood, then we can and do that by reacting with it, then we can maybe identify these chronic diseases too. But this is in its infancy. Right now, it's still probably 5 or 10 years away from actually being useful. What is your projection of how long it will take to move these exciting techniques into human health applications? Well, that's been I'd like to make sure that they're available to me when I get older. And so the clock is ticking, actually. And so what we need to do, that's why I think companion animals are particularly attractive. If we can convince our friends in the animal clinics and vet offices that these devices are useful, which they can be, especially if they're just diagnostic devices and not therapeutic devices, then there's actually no need to get FDA clearance for a lot of these systems. And so long as a vet is in charge of implanting them, I think we can gather a huge amount of data that will then accelerate the clinical acceptance of these devices. Then how is the glucose sensor securely embedded? Is there concern about movement within the tissue? That's a really good question, and it actually depends on the tissue. So in muscle tissue, sometimes it moves around. In other tissue, it behaves like a tattoo. So think about a tattoo that doesn't move very much because it's very close to the underneath the skin. And so very similar to our devices, we'd like to embed them in those areas which don't move. What cycle threshold values for SARS-CoV-2 tests can you detect in our low-cost PCR machine? Are we using the N gene primers? We've actually used the N gene, the S, the O, many different assays. The interesting thing is the N1 and N2 is not really a fantastic assay, even though it was developed by the CDC. But the idea is, you can use pretty much any of them. Right now, for FDA approval, we're going through the N1 and N2 CDC assay. But the threshold, the cycle threshold that we've measured, the LOD, if you will, is in the upper 30s. So we've measured samples that had clinical samples that had CTs of upper 30s. We think that we can do better than what the conventional capabilities are in the laboratories, mainly because we don't throw away any samples. So if you go into the laboratories, and I actually went to work in the University of Missouri pathology lab for a while to try out our system. 4/5 of the sample is thrown out essentially, or not used when you go through sample extraction. And then another 4/5 is not used for the amplification. So about 25 times, 1 part out of 25 is actually used. And so that decreases the sensitivity. And so we're actually we're using all of the samples. So it may make us much more sensitive, up to 25 times more sensitive if we're lucky. And then last question. What are the barriers of reducing the cost of the machine further? I think there is a great opportunity to shrink the cost of a PCR machine further. If you compare it to a DVD player, and a DVD player, if I go to Walmart or wherever, I can buy one for $50. There is so much more technology in a DVD player than in a PCR machine. We can certainly go down to that scale if we are serious. Right now, of course, we're trying to address the problems of the day, And $2,500 seems like a reasonable cost for a system like this, especially if it gives you answers in 15 minutes. But I think down the road, we will see these instruments and this technology go down to sort of the $200–300 level. Then last question, do you remove the chip after it is no longer functioning? That is one of the key questions that I'm sure the FDA will ask us. So what we have done is redefine functioning. So what we do is on every chip, we actually include a temperature monitor. So the temperature monitor lasts as long as the electronics does, which is about 30 years. And so we can measure body temperature all the time. So if the glucose monitor does not work anymore as a glucose monitor, it will be a temperature monitor, and it can be used to look at peripheral arterial disease and other things that look at the efficiency of the circulatory system. So I hope I'm sure I missed some questions, but I hope I've addressed a couple of them.
Thank you for a wonderful lecture, Axel, and inaugurating the IDS lecture series. Thank you all for attending, and I hope you enjoyed the lecture, and we hope to see you next time in the next IDS lecture. Bye-bye.